Okay, picking up where we left off, we left on page 120. We're talking about how the request for comments procedure is long and kind of tedious, and some people just call them perpetual betas because things just take forever to happen. And most companies, for example, when the new wireless standards came out, then we had the 802.11b and C and N and AC. An awful lot of the manufacturers actually started producing wireless cards using the new standard before the standard was actually ratified. It just takes so long. They figure, and if you're a device manufacturer, you could probably say, well, look, we're going to go ahead and say it's compatible with the new AC. And if it turns out that there's some last minute change, well, then we'll just fix it with a patch. Okay, so that's kind of their thinking. Now, the whole point of IP was that it would run on top of practically anything. It doesn't matter what the layer 2 you had. This thing was designed to fit inside a layer 2 packet. So this happens to look like these are all Ethernet links, but it didn't have to be. There's another little diagram coming up that'll show this in a little bit more detail. So the saying is that, and I have to turn on my fake Texas accent for just a minute, so forgive me. You can run IP over a barbed wire fence. The meaning being, you can run IP over any type of layer 2 encoding. It doesn't really matter. IP is so universal that you can send it over a serial line. You can send it over USB. You can send it over Bluetooth. You can send it over Wi-Fi. You can send it over fiber. You can send it over coax. Blah, 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 blah. Point to point. Doesn't matter. It was designed to one size fits all. It was designed that it was quite literally designed that everything at layer 2 would work. Because that's its purpose in life. Is take a layer 2 packet from over here and make that layer 2 packet show up over here by some sort of a routing option. So it has to take all the layer 2s that exist to be able to pull that off. So it's extraordinarily versatile. So let's talk about the history of how all this happened, because it's somewhat important. Back in the Unix days, the first routing was basically just files and email, things of that nature. I would send an electronic email, hit the button, and it would just copy a file from one machine to another. And files are not that difficult because I can send email as a file. I can send files as files, right? And then much later, the web came, and that kind of changed a lot because now, well, in the beginning of the web, there was no difference whatsoever. It was just a contextual way of describing documents that you could get over the web, over the internet. So the actual mechanics of how you got it weren't all that relevant. But then, of course, things changed because the web threw in, audio signals and pictures, and then after that, we got video over the internet. And so, the people who wrote the IP address protocol back in the 80s, when only thing we were doing was sending email, they were pretty doggone smart because the IP has survived. It's survived through, video and all those extra things that they had no idea were going to exist. I mean, this thing is so versatile, it's future-proof. Okay, that's the point. Okay, so let's continue. Now, there are some limitations with IP. IP is not the greatest thing since sliced bread for everyone. Okay, the number one thing is the IP address, IP protocol rather, does not actually guarantee that the packet is going to arrive. I mean, look, at this example here, let's just pretend. Let's say that I'm doing maintenance on this web server and I have this web server turned off, okay? You're over here and you don't know that the web server has been turned off. So you fire up your browser and you type in a URL and you hit the button and your machine is blissfully ignorant. It sends the link to this guy who's equally ignorant, who sends the link to this guy who's equally ignorant. sends the guy to this guy, and this guy says, wait a minute, that guy he's not responding. There's something wrong. So the links going all the way across don't really have a way of saying, dude, I'm not ready, or dude, I'm shut down, or dude, don't talk to me, do not disturb sign, hung up. So it's not designed for making sure that all those things happen. Now there is a technique to do that, and that's layer 4, which is the next chapter. Okay, so I'm not talking about it doesn't exist. I'm saying it doesn't exist in this layer. Okay, doesn't exist in layer 3, which is what we're at, chapter 4. Okay, so what it's called is, often when you're using described as, it's described as the best effort to get the packet to where it belongs. But that's about it. If you didn't get it, or there was the router, let's say this router is being hammered, and so a packet just got lost. Okay, so now the web server is up and running. Okay, let's don't make it too complicated here. This router is way overtaxed, and so a packet just gets lost on the way. It just disappears. Poof. Okay, so I don't ever get that packet get sent, or perhaps on the way back. So it's not the responsibility of IP to say, whoops, I'm missing that packet, let me send it over again. That exists, but does not exist inside IP. Okay. And there's a practical limit on the number of hops you can have, how many links you have in between. It's 256 hops. Now, that's not normally a bad thing, because people have studied this on the average length, the average number of hops for internet traffic, okay? And it's about, somewhere in the range of 12 to 15. Yeah, you can have 30 or so, and 40 if it's way, far away and has to go through convoluted routes. But so far, no one has complained that 256 is not enough for the number of hops to get from point A to point B. So I'm guessing most likely it'll never get to there. Okay, so an IP packet, the actual IP packet on page 122 looks like this. I'm going to zoom in on that just a tiny bit. Okay, so the IP packet lives inside a layer 2 packet. Layer 2 in this case, let's just say it's Ethernet to make the conversation easier. Okay, now this is a concept that you're just going to have to get, okay? And the question is, these things are like nested, the what's called Russian dolls. You have a Russian doll, and you open it up and there's another one, you open it up, there's another one, another one. Okay. Or the analogy could be a candy coating. You have something and you have a candy coating, and then you have another candy coating on top. Bottom line is, the order in which the candy coatings or the Russian dolls are stacked, or the cardboard boxes, or whatever metaphor you would like to describe this is an important concept that I really want you to get. Okay. And it goes like this. Every single protocol in this stack, let's just talk about the TCP/IP stack. Okay, let's talk about that. Over Ethernet. Yeah, every single one of those, every stack, every chunk is embedded into the next one, into the next one, into the next one. The outside candy coating in that example is Ethernet. That's the outside candy coating, because that's the only thing that layer 1 knows how to deal with, right? I mean, if I have an Ethernet cable and I'm trying to talk Ethernet over it, it'll work. If I have an Ethernet cable and I'm trying to talk IP over it, it's going to say, I'm sorry, I'm an Ethernet cable. What the hell are you doing? So the outside candy coating has to be Ethernet. That's the only thing Ethernet understands is Ethernet. The next one inside is going to be an IP packet. So the payload of an Ethernet, in this example, the payload of the Ethernet frame is an IP packet. But wait, there's more. Said in an infomercial tone of voice. Inside the IP packet could be a TCP packet, and it has a payload of data. Okay, so outside edge, and then it goes up the pyramid, so to speak. outside being the bottom layer, layer 2, and then layer 3 gets inside that. The next, go up the OSI one more time, and whatever the protocol that is goes inside to that. So it all stacks up, which is what we're trying to talk about. Okay, so in practical terms, in this example, using Ethernet, the IP packet is inside the Ethernet, not the other way around. Okay, so now they talk about the header. They're going to go into some detail about this header, and I'm not really going to beat you up on, what's at bit 14, that kind of stuff. So first, I just want you to eyeball this thing, okay? Just kind of eyeball it. And if you're a programmer, you're going to notice something that's kind of cool here. And that is, everything is aligned to 32 bits. Now, if you recall from last time, the last chapter, we're talking about Ethernet. I mean, they had, 7 bits for this and 3 bits for that. I mean, it was designed for hardware, and hardware basically doesn't care. This was designed for software, and software does care. It makes it so much easier. For example, the difference, it's easier to have a byte and then split it in half, or to have, 4 bytes and have 1 byte, 2 byte, 4 bytes, all multiples of 2. So the software people are the ones who came up with this standard. You can probably kind of sort of tell that the hardware people had their hands in the Ethernet standard. Okay, software people had their hands in the IP. Okay, just checking. All right, so I am going to describe these things, and again, the order in which they appear, and some of the technical details is not what I'm going to be asking you about. I am going to be pointing out some things that I think are kind of cool that we'll be talking about later. So let's just start. So the version number. This could be a 4 or a 6. 4 meaning that the rest of this header is designed for the 32-bit addresses. By the way, this example we're looking at is an IP4 header. The IP6 header looks a lot different. Okay. So this could be a 4 or a 6. And then the header length. And you might think, well, why do I have to tell you the length of the header when isn't it pretty obvious? Well, no, believe it or not, it's not. These things have options. You could just, this optional field, you can put just more stuff in it. And quite frankly, you could actually just make this thing as kind of sort of as big as you want. And I know a lot of companies kind of took advantage of this and to add like VPN services and all sorts of interesting things where they can embed a second set of destination and source IP addresses into the frame. Kind of cool. And then, of course, well, let me just go down the list. So the length of the header is kind of sort of important. The type of service. This is back in the days when they were considering, quality of service, like, this is a real-time audio video stream, and therefore it's more important than your file transfer. And the file transfer is more important than your email. So some sort of a ranking system. The total length. This is the total length of the frame to include the basically the header and all. Everything. To include the data. So, all right, mathematicians. If I have 16-bit number, what's the biggest size, what's the largest 16-bit number for you computer people out there? Well, it's 16,000 blah, 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 blah. So 16,000 bytes, 16K bytes is the maximum you can get for an IP frame. The next one talks about the identification and flags and fragment. Those are all when I'm having to break this thing apart and put it back together, and I want to make sure I got the same sequence going on. That's what it's about. And I guess this is a good place to stop for the 15-minute mark, and we'll pick up this conversation again in just a few.